the previous two lectures, we have considered two cases, one of a particle moving in a delta function potential and a particle moving in a finite size box, for which the Schrodinger equation could be solved analytically. However, all potentials are not amenable to this kind of treatment. For example, even if I take a potential where the potential becomes infinity at the boundaries, let us say x equals 0 and x equals L, but change the potential in between, suppose it is like this, or a potential which is like this, or in general a potential which is some arbitrary shape in between. How do I solve the Schrodinger equation? And for that we have to numerically integrate the Schrodinger equation. How do I numerically integrate a differential equation? I will right now focus principally on solving the Schrodinger equation, which is a second order differential equation, psi double prime plus V x psi equals E psi, and this is an eigenvalue equation. That means I have to satisfy certain boundary conditions, then only the solution is acceptable. So, let me just review that. For the Schrodinger equation, minus h cross square over 2 m psi double prime plus V x psi equals E psi, I am supposed to, number 1, satisfy certain boundary conditions. The wave function psi x is continuous, and third, psi prime x is continuous unless v goes to infinity. So, I have to satisfy all these three conditions, and then this together gives me the eigen energies and eigenfunctions. So, what we need to do is solve this equation satisfying the boundary conditions and making sure that psi and psi prime both are continuous. To start learning about numerical techniques, we will focus in this lecture on a simpler problem where psi 0 is 0 and psi L is 0. That will also make us understand the problem better. So, this is the problem with infinitely high walls, V goes to infinity at 2 points and remains infinity outside. Between 0 and L, V is some shape V x. So, psi is 0 at this edge and psi as 0 at the other edge, and we have to build the solution in between. So, in numerical solution of differential equations, we actually construct a solution. How do we do that? We start integrating the psi prime and psi double prime to update our size and all that. So, one technique could be in this case, in which case the psi is 0 on two sides, psi 0 and psi L both are 0, this is x equals 0, x equals L. So, one way of constructing could be start at x equal to 0 with psi 0 equals 0 and psi prime 0 equals some finite number, let us say 1 or some constant. I will keep showing what I am doing here. So, in this box I have, let me show psi by red, psi equals 0 and some slope. What we can do with this is find the value at the next point. So, number 2, from the Schrodinger equation, psi double prime is equal to V 0 minus E 2 m over h cross square times psi. So, I know this implies that at any point I know psi and psi prime, it gives me psi double prime also. So, from this point on the left hand side, start at x equal to 0, I have updated, and so I can write psi at the next point, let me call it I plus 1th point, is equal to psi at point I plus psi prime delta x. And I can also update psi prime at I plus 1th point as psi prime at ith point plus psi double prime delta x. And how do I know psi double point? If I know psi at some point, I know psi double prime also. Once I do that, so I have found everything on this cross. From here, I again build my solution to the next point, and from that to the next point, from that to the next point, from that to the next point, and so on. I can keep building the solution. Because I am keeping terms only up to the first order, I have to make sure that this delta x is really small in the second order, can be neglected. Now, once we start with this process, so in this case I am taking the case where the psi vanishes at both sides, psi equals 0, psi equals L. So, start at x equal to 0 with psi 0 equals 0, psi prime 0 equals some constant. So, let us write it C, I wrote 1 earlier, and build up the solution up to x equals L. Now, boundary condition demands that psi L be equal to 0. Remember now, when I am starting from psi equal to psi at x equals 0, I am building up a solution, and the solution depends on E. How does that happen? Because I had a psi 0 equal to 0, psi prime equal to 0, but I have psi double prime at any point which is given as 2 m over h cross square V 0 minus E psi. So, depending on what E is, psi prime is given, and I use all these 3 to build up my solution. So, psi L is not going to be 0 until I really have that eigenvalue. So, what could happen? For example, if I build up the solution, one solution could be like this. I am showing in green, this is not acceptable. So, this is some E. Second solution could do like this, some other E. Unless I have exactly the right E, that it goes to 0 on the other side, and that is acceptable. So, if psi L is equal to 0 for some E except that E as the eigenenergy and the solution psi as eigenfunction. And then you can keep increasing E and find more and more and more states. Since the particle is bound in this case between 0 and L, that means V goes to infinity outside this boundary, there are going to be infinite number of states in this case, and so you can keep scanning over E and find more and more states. The other method could be again using the properties of the solution of the Schrodinger equation. In this case again I have psi 0 equals 0, psi L equals 0, x equals 0, x equals L. Number 1, start integrating, or what I say, building up the solution. From x equals 0 to the right. By right means x greater than 0. So, you start with psi 0 equals 0, psi prime 0 equals some number, and then you know psi double prime from psi, and you start integrating out up to certain point x, let us call it x 0, up to x equals x 0. Second, start integrating, again building up solution, from x equals L to the left. So, what you will do is psi at x equals L is 0, take psi prime at x equals L to be some other constant c 2, psi double prime I know. So, you start again integrating to the left and up to x equals x 0. So, what have we done? What we have done is, in this potential, we have started building up a solution from here. Let us say this is what comes out from this side, and we started building up the solution from the right side, and let us say this comes out like this. It need not match. The other situation could be that, let me show it in red, this fellow could be like this. What we should do is, at x equals x naught, the solution should match. What does that mean? At any point, what do we have for the acceptable solution? Psi x is continuous, that means psi x equals x 0 from left should be equal to psi x equals x 0 from right. And number 2, psi prime x is continuous. So, you should have psi prime x equals x 0 from the left is equal to psi prime x equals x 0 coming from the right. So, what you could do is match the two solutions first by multiplying by a factor and then compare the psi prime values. So, again let me make this picture, and you have a solution coming from the left which could be like this, solution coming from the right which could be like this. Now, let us see if at this point where I am matching, which is x equals x 0, since we started with different slopes, first the wave function need not match. So, what we need to do is multiply the right hand side with a factor that brings it down, makes the wave function match at this point. So, I can write psi right at x, I could write as psi right at x times psi left at x 0 divided by psi right at x 0. This will make the match. So, this will make the curve to be this blue one, right. So, let me write this new. So, from red we have done this one, let me write this one as red. So, I have made psi right new x equals psi right x times psi left x 0 divided by psi right x 0. And then after that, this is step 1, and after this see if psi prime left x 0 is same as psi prime x 0 coming from right. If it is not, the solution is not acceptable. On the other hand, if the two are equal, then we have found the eigenenergy E. So, for some energy they are equal, and that is the eigenenergy. They will not be equal for all energies after all this rescaling has been done. So, this is the way to find eigenvalue and the eigenfunction in two different ways. One, by making sure that the wave function is smooth all over, that means psi and psi prime are the same no matter which side I integrate the wave function from, and the other, I build a smooth wave function starting from one boundary and make sure that the other boundary condition is also satisfied. Both are acceptable ways. Now, we sometimes combine, in fact not sometimes, all the time combine the continuity of psi and continuity of psi prime x in one condition known as the continuity of logarithmic derivative. So, in this case what I do is I take psi prime x 0 over psi x 0 left and compare this with psi prime x 0 over psi x 0 coming from right and check if they are equal. If they are equal for some E, we have found the eigenenergy E. If not, we again go to some other energy and check. So, we scan over the energy and see what happens. So, these are going to be the two methods which we use in calculating the eigenfunctions and eigenenergies of a given problem. And right now, as I said earlier, we are focusing on problems where the potential could be anything between x equals 0 and x equals L, but it is going to be infinity outside that region. So, that the wave function is always going to be 0 at the two boundaries. Now, the Schrodinger equation is minus s cross square over 2 m psi double prime plus v x psi equals E psi. Now, these numbers h cross and m are very small, we are dealing with microscopic world. So, it is good idea to rescale the problem so that the distances and energies are of the order of 1, that means we are changing units rather than of the order of being 10 raised to minus 36, 10 raised to minus 19 and so on. That will be very difficult to program in a computer. So, what we do, for example, in this case, in the case of the problems that we are dealing with right now, is that length scale we will take to be L, that is the width of the potential, and the energy scale naturally becomes h cross square over ml square. So, we will keep the length scale to be h cross square over ml square, which is dimensionally correct. So, let us rewrite the Schrodinger equation for this. So, when we do that, we have minus h cross square over 2 m d2 psi over dx square plus Vx psi equals E psi. Let me multiply here by L square and divide by L square, so that I have the equation as minus h cross square over ml square 1/2 in front d2 psi over d of x over L square plus Vx psi x equals E psi. Divide by h cross square over ml square all over to get minus a half d2 psi over d x over L square plus Vx psi x, this is divided by h cross square over ml square, is equal to E over h cross square over ml square psi. Call y equals x over L and E bar equals E over h cross square over ml square and V bar equals V over h cross square over ml square, to rewrite the equation as minus a half d2 psi as a function of y over dy square plus V bar y psi y equals E bar psi y, and that is my equation in these dimensionless quantities y, E bar and V bar. And now I can take y between 0 and 1 for x varying between 0 and L. Remember, in quantum mechanics or in atomic quantities, L is of the order of maybe a few angstroms, which is few 10 raised to minus 10 meters. Now, I can vary y between 0 and 1. So, I can take the increment in y to be of the order of 0.01 and so on, whereas if I were to do the same thing in terms of x, it would be much more difficult and numerically unstable. So, now we are ready to integrate the equation. So, I have again I will take this box where in between there is some potential, let us call it V. Now, y, this is given in units of h cross square over ml square. So, I am going to drop that bar and just write this as minus 1/2 d2 psi over dy square plus V y psi y equals E psi y. Method 1 is going to be, remember what we did, we start with psi as 0 equals 0, take psi prime equals some number, let us take it to be 1 and then integrate. So, what we will do is we will divide this whole thing into small meshes of interval delta x. So, delta x could be of the order of 0.01, 0.005 or so on, all right, some delta x, very small number. So, I start from psi equal to 0 and psi prime at 0 equals 1, psi double prime by the Schrodinger equation, which is 2 v minus e psi. Then I have psi at delta x would be 0 plus psi prime at 0 times delta x. Psi prime at delta x is 1 plus psi double prime at 0, which is 0 right now, delta x. And now I can write psi double prime at delta x to be equal to 2 m v at delta x minus e times psi at delta x. This is one cycle completed. From here I can go to the next step and write psi 2 delta x would be equal to psi delta x plus psi prime delta x delta x. Psi prime 2 delta x is equal to psi prime at delta x plus psi double prime, which we have already calculated at delta x, and psi prime 2 delta x is now updated to be equal to 2 v at 2 delta x minus e psi at 2 delta x. This is another cycle we have completed. This m should be going away, and now I can build up the solution and so on. So, in general what I am doing is I am writing psi at I plus 1th point to be equal to psi at I plus psi at I prime times delta x. I am updating psi prime at I plus 1 as psi I prime plus psi I double prime delta x, and once I have found psi at I plus 1, I can update my psi double prime here, plus 1 is equal to psi at I plus 1 times 2 v at x I plus 1 minus e. Notice that will depend on e, and this way I can go all the way building up the solution at different points all the way to the other side, x equals L, and then check if psi, let us say the last point is n, is equal to 0. Now, numerically it is very difficult to make sure it is 0. So, what you do is you say psi n modulus is less than some very small number, let us say 10 raised to minus 3 or 10 raised to minus 4 or so on. If that is the case, you accept it. So, the moment that happens, you have found the eigenenergy E. Whichever E that happens for, you have found that energy, and once you have found that energy, you have also found psi. Psi I at different i's, I equals 1 through n, gives you the value of psi at each point. So, now you normalize psi. What do? You calculate integral psi mod square dx 0 to L, which will be nothing but summation I mod psi I square delta x I equals 1 through n, and this gives you some number, let us say C n. Then psi I nu is equal to whatever psi you calculated earlier divided by square root of C n, gives the normalized wave function. That is one way of finding the wave function in this case. Method 2, which in this case is not really required, but I am giving it because it will be required for cases that we will discuss in the coming lectures, In method 2, you actually start building up the solution from one side, you start building up the solution from the other side, and you match the logarithmic derivative at some point x 0. Once that matches, that gives you the eigenvalue. So, what do you do is some potential in between, you have psi L equal to 0, psi 0 equals 0. So, you start, you again divide this whole thing into small intervals. So, you write psi I plus 1 equals psi I plus psi prime delta x, and all those steps that we did earlier, and integrate up to x 0 from x equal to 0. This done, let us say the last point is n, then you go psi n minus 1 equals psi n, which is 0, plus psi prime n times minus delta x, because you are going left. So, this is going to be psi n minus psi prime n, whatever value you assumed, times delta x. You go psi prime n minus 1 equals psi prime at n minus psi double prime n delta x, and then you update psi double prime, and so on. So, you build up the solution the other way, and then check at x equals x 0 if psi prime over psi left is same as psi prime over psi right. How do we check that? We can say that psi prime over psi left minus psi prime over psi right modulus is some less than 10 raised to minus 3 or 10 raised to minus 4, that you have to play around and see where you get the answer. Once that happens, if it happens for certain E, that is the eigenvalue. So, for E's, when this happens, you have found the eigenenergies, and the corresponding psi. Now, to make the psi proper, what you do is, you have come from left, you have come from right. So, what you do is psi right at some x nu has to be equal to psi right at x times psi left at x 0 divided by psi right at x 0. This will make sure that now the wave functions match at x equals x 0, and then you found a continuous wave function and you can normalize it. So, what I have given you is, in this very specific kind of problem where the wave function vanishes at the two boundaries, how to find the wave function and the eigenenergies. So, to conclude, we have learned about integrating the Schrodinger equation for very specific problem where V x is equal to infinity for x less than equal to 0 and x greater than equal to L, and is equal to V x for x in between. So, psi 0 is 0 and so is psi L, and we found a way of finding the solution. We will now, in the next lecture, consider cases where psi does not vanish at these boundaries, but goes all the way to infinity. How to find solutions for those situations.